Hello everyone and welcome to the channel. In this video I will work through a number of cleanups and refactorings I wanted to do for a while before adding any new functionality or hardware to the circuits. We can call it a spring cleaning if you will. So I hope you enjoy. Okay, so I want to do a quick refactoring. It's very tedious to change the string here. I want to change it to a loop. I also want to print it on the LCD as well, so that I can see visually when I'm working on the breadboard that everything is working. So I'm going to create another routine here. I'm going to call it ACIA and LCD put char, and it's basically going to do this. And then we can just our ACA and LCD put car here, and also everywhere else except the carriage return and the new line, because we don't do that on the LCD because the LCD doesn't support those characters. Okay, let's see what it does. Programming, post routine, and then it's printing the string. All right, perfect. Now let's move this to a loop. Okay, let's see if this is going to work. Nope. Ah, yes, I know what's wrong. My registers are not preserved on subroutine calls, so I have to save the X register here and restore it after. And it works. Let's do hello YouTube. Perfect. So I kind of got frustrated with switching back and forth between the Arduino IDE and my usual editor, which is Visual Studio Code. And so I wanted to integrate the Teensy monitor into my main editor. And so I did that by migrating to PlatformIO, which is a development environment for microcontrollers that you can configure to work in Visual Studio Code via an extension, and you can also use it with command line tools. And so now that I have this configuration here for my Teensy, I can edit and compile the Arduino monitor code directly in Visual Studio Code, and I can upload by running this command. This will compile and upload the code to the Teensy, and you have a nice progress output with a bunch of debugging information if something goes wrong. And I can also connect to the serial monitor on the Teensy. And as you can see, I've added some help information here, but basically I can do what I was doing on Arduino, except I also don't have to press send every time I send a character. So now I can just type R for reset. You can see the CPU is reset. I can do T for trace, Q to stop the trace, and I can also see the output of programming the EEPROM. So if I program the EEPROM here, you can see that the output is now here, and I can wait for it to work just like that. And so overall, this is much better and much more integrated, and this is going to make me more productive. Now, the next improvement I want to make is related to tracing. So you can see here I'm tracing the program execution. I have the contents of the address bus, the data bus, and whether it's a read or a write, and the star means it's an opcode fetch. So it would be nice to decode this opcode to see what the CPU is actually doing. And so I've added a list of all the instruction mnemonics, which are indexed by the opcode. And so now the Arduino can know that, for example, the first one is break, then we have OR A with this addressing, etc., etc. And so these are indexed by the number in the opcode. So there are 256 of them. And I'm making use of this array here. If the sync signal is set, then we print the contents of the mnemonic to the serial console. And so this will replace the star that we're currently seeing in the terminal. So let's try this. So let me quit the monitor. I'm going to run the upload task. This will program the Teensy with the new code. And then we can go into the monitor again. There we go. Let's try tracing. And yeah, as you can see, we now have the decoded instructions. So of course there's no fancy parsing and formatting. So for example, I'm not decoding the contents of the address in this bit instruction. I just know that 2C is a bit instruction with an address. But this will help us get situated when we are troubleshooting code. So for example, if I reset the CPU here and then quit, we should be able to find here the reset sequence. We can see here it's loading the reset vector, and then it's going at the start of the code. And then if I open in my editor the report from the assembler, you can see that we can follow. Here we have a load X, then we have a transfer X to S, CLC, XEE, etc. And so this is going to be much more useful now. Next thing I want to do is work on some optimization on the TNC monitors. So I've attached an oscilloscope probe to the clock, and you can see here the clock is currently at 3.33 megahertz. That's the output of the debug clock with the divider that we have set up. Now if I go to my TNC monitor and I start tracing, the TNC will take over the clock and run it as fast as it can, but it's going to be pretty slow. So let's start tracing. And as you can see, the clock is now averaging around 1.9 kilohertz. And that's because between each clock pulse, the TNC has to send the text content of what we see here in the tracing window to the computer over serial. And that's going to be pretty slow. So I want to see if I can optimize this to go even faster, because then it's going to make the debugging experience even more useful. The first thing that we can do is we can remove this binary section, because I mean it was useful at the beginning when we were setting up the circuit, but now we probably just want to see the hexadecimal values and the opcodes, but having the raw binary doesn't make any sense, and it takes more than half of this text here. So this is going to split it up pretty quickly. So I'm going to add an option here at the top called binary trace, and we can enable that if we want to see the binary again. There we go. Now let's see what it does. Let's start tracing, and as you can see, we're now at an average of 5 kilohertz, so that's a pretty nice speed up, almost 3 times as fast, but I think we can do more. The sprintf function is actually pretty slow in Arduino, and it's often recommended that you actually use direct calls to serial prints instead, because these directly put the text into the serial buffer, and sprintf has a bunch of formats and thing that it has to do that's quite complicated in order to generate the text. So if we replace this call, I think we can improve the speed a little more. And I make use of my printbyte as hex function, which is also just directly calling serial.print. So let's see what this gets us. We actually have to move it before this function. And that's another pretty nice speed up. We are now averaging around 6.7 kilohertz, up from 5. And finally, we can turn on some optimization. If you look at the verbose output during compilation, but you can see the call to the compiler here. You can see that it's using the -OS, which is optimizing for the size of the code and not for the performance of the code. But we have plenty of memory left in the flash on the TNC, and so I think we can use optimizations for speed instead. And we can do this pretty easily in our platformio.ini file. We just have to unflag the size optimization and add -O3, which turns out the maximum optimizations for the compiler. Now let's see what that gets us. Let's start tracing, and yeah, we're now at 6.9, which is even faster. So that's pretty good. One of the things that has been bothering me with the build is that there was currently no easy way to move the breadboards around my lab, and it's sort of always been quite painful, as you can see. So I've decided to create a support for the build by just using a piece of plywood and I'm going to add some angled brackets to hold the breadboards. So these are brackets that you normally use to fix sagging drawers, so you can get them at the hardware store. And yeah, these are going to help hold the breadboards in place. All right, there we go. Okay, so for our next subject, I want to look at the debug clock. So in a previous episode, I've done this calculation here to determine the maximum frequency, and it involved tracking the falling edge of the clock through U18 multiplexer, then to this flip-flop over here, and then through this multiplexer. And I think there's an even better solution. That's what I found here. We are using two multiplexers here, U17 and U18, but we could replace both of them with a 153. And I'm going to make that AC version for now. We can take our run clock here. That's going to be selected between slow and fast. And we need to duplicate those bits here because we're going to use something else for the second selection bit, and that's going to be the pulse and run selection. And of course, the run clock can't change when we change the second selection bit here. And then we can move this section. So slow and fast are the same, but then we have pulse clock here. And then both the enables are connected to ground. And that's going to be the output clock. So we can replace the AC151 with the AC153. And then over here, we don't need any of the selection bits anymore. We can just use out clock as an input. And everything else we can connect to ground. And we can keep this chip because it's actually the only chip I know that's able to buffer and invert a signal at the same time and have a tri-state output. But because the clock selection happens here, this is now not involved anymore in the maximum speed of the clock. And so we go from a maximum frequency of 6.8 to 12.55 megahertz for the fast clock. And similarly, we can update the other computations. Okay, so now that this is simplified, we can go back here to the fast clock, and we can remove this adder here, which will multiply the maximum frequency by 2. And so that's going to go to 10 megahertz, which we can now do with our new multiplexer setup. So let me remove this chip here. There we go, and then the new divider settings become, there we go. Okay, so the next thing I want to have is I want to have LEDs for which speed and which mode the clock is currently in. So I'm going to wire an LED here on the pulse and run selection bit, and I want it to be lit when we're in the pulse mode. So if we are, this is going to be low. There we go. And on the fast and slow select, we need to take into account the state of the pulse and run bit. So I'm going to add a NAND gate. Actually, no, that's going to be an OR gate. When this signal is low, we're in the run state. And when this signal is low as well, we're in the slow clock mode, and so this is going to be low. And so we can take this LED here and copy it over here. And this is going to be slow clock. And then we need to take the inverse of this, like this, and it's going to come from here. And here we're going to be on the fast clock. Let me make some space here. Now this can be the LED section. There we go. Okay, this should work. Okay, so let's start by redoing the output stage. So we can remove the 74151 that we have in the circuit. And I have here the 153 that is going to be in the replacement. So let me first remove all the wires. So power and ground is already there. Then we need pin 1 and pin 15 pulled to ground. So this wire here is the fast and slow selection bit. And we need this to go to pin 14. Now the second selection bit is pulse run, and this comes from the bottom flip-flop here, and it should go to pin number 2. There we go. Then the run clock is at pin number 9, and it goes to pin 1 of this flip-flop here, that's the green wire. There we go. This is the slow clock, and it goes to pin 6 and pin 10. So this is pin 6. This is pin 10. Now this is the fast clock, which goes to pin 11 and pin 5. Then we're going to need to connect 10 to 12 and 11 to 13. There we go. Then we need the pulse clock on pin 3 and 4. That's the white wire coming here. There we go. And finally, the output clock is on pin 7, and it goes to pin 4 of the output multiplexer. Okay, so these are all the pins of the 153 connected, and now we can do the output multiplexer. We need to connect pins 1, 2, 3 together and to ground, and then 15, 14, 13, 12, 11, and 10. This should be everything. The clock should work properly now. This is fast mode. We can select the mode, and this is the pulse clock. And I can select the slow clock as well. Yeah, everything works properly. Now we can remove the adder here. Okay, and we just have to reconnect the dip switch to the counter. Okay, should be everything connected. Let's get the oscilloscope. Okay, so let's measure the frequency. With everything off, we should have 10 megahertz, which is right. If I bump up the first bit, we go to 5 megahertz. Then 3.3, that's correct. 2.5, 2, etc. So that's great. So this works as well. I can probably move back the oscillator to this spot here. Alright. Okay, so now let's do the mode LEDs. So I have here 7432. So we'll have one not connected to the OR gates, that's the pulse LED. And then we'll do 8 for the fast LED and 11 for the slow LED. So my LEDs have built-in current limiting resistors. Please remember to add some on your LEDs if they don't. Now the pulse run signal we can get on pin 6 of this flip-flop here. And the inverted is on pin 5, and we need to bring this to pin 9 and 12. Then from the top flip-flop here, we need the fast high signal on pin 9. And then on pin 7 we have the fast low, which is gonna go to the other OR gate. Okay, let's try changing. So if I go here, I go to the pulse mode. And if I change the speed, yeah, that works. Perfect. And here we have a little label that shows whether we are on the fast, slow, or pulse clocks. Perfect. So the next thing I want to fix is this inversion that I made here. I'm taking the clock source from the inverted output of the debug clock. And the reason for that is the debug clock is currently set up to switch when the clock is low. And so the pulse clock defaults to a low state, but it's not really useful because the CPU outputs and reads data when the clock is high. And so in order to see something on our LEDs, we need the pulse clock to default to high. So I've inverted it here, but I think if we switch this back and make the fix in the debug clock itself, it's going to lead to a bit of a simplification. So let's do that now. So in order to change when the debug clock is switching, we only have to change those 3 flip-flops. I'm currently using JK flip-flops that are negative edge triggered, so they trigger on the falling edge of the clock, but we now want them to trigger on the rising edge of the clock. And so to do that, we can just replace them with 74 HC74s, and that should do the trick. This means that the clocks will now switch when they have a rising edge, and we also need to invert the pulse clock so that it defaults to high when the button is not pressed. So I'm going to take this inverter here and I'm going to put it here. I'm going to use it to invert this. And then for the clock LED, we can buffer it using one of our spare OR gates here. And of course, the polarity is now inverted. There we go. And in order to make the wiring a bit easier, we can actually switch this around. There we go. And there's probably a way to rearrange the passive components here in order to do this with a single inverter, but for now I'm lazy and I will just use the spare one that we have. Okay, and then we just need to replace the JK flip-flops with regular D flip-flops. There we go, and in order to satisfy our timings here, we need the last ones in the chain to be a faster variant. So I'm going to use AHC chips here. So before I go and wire up these changes, there's one more thing I need to fix on the selection bits, and it's related to crossing clock domains. So if you look at this arrangement here, we have actually 3 different clock domains. We have the fast clock, the slow clock, and then clock that is equivalent to you pressing the speed button. And if we look at this last flip-flop here, it's triggered by the rising edge of the fast clock. And this being a flip-flop, it has a setup time and a hold time requirement on the edge of the fast clock. What this means is the input data needs to be stable during an interval around the rising edge of the fast clock. If the input data is not stable because it's changing, then the results is undefined. The output could be high, could be low, or it could be in the middle of both, meaning an analog voltage that's not a valid logic level. And if that's the case, then it will propagate to the multiplexer here and potentially to the output clock. So if the data here happens to be changing right as there is a fast clock rising edge, then we could potentially have a glitch in the output clock, which would make the computer unstable. Now, the same is true here on the middle flip-flop. If the data from the speed button is changing when the slow clock has a rising edge, then we could have an unstable state here. It's called metastable. So we could have a metastable state here that could propagate through the flip-flop and into our output clock. So the way to fix that is a technique called double flopping, and I will recommend this great article on the allaboutscircuits.com website, Introduction to Clock Domain Crossing, double flopping, that goes into this problem in detail and shows the solution that is double flopping. And what double flopping means is we can add a second flip-flop triggered by the same clock signal, and this means that it will give the metastable signal some time to stabilize before propagating to the rest of the circuit. So let's try this now. So this is the new circuit. Now, if there is metastability at the output of this flip-flop, or this flip-flop, or this flip-flop, because we have two flip-flops triggered by the fast clock rising edge here, the signal will have some time to stabilize, and that's going to be the interval between two rising edges of the fast clock. And that's generally enough. The time needed for the signal to stabilize is counted in nanoseconds, and fast clock period is going to be a maximum of maybe 100 if we're going with 10 megahertz. And so that's going to be plenty of time for this signal here to stabilize and then be propagated at the next rising edge of the fast clock. And the same thing applies here for the same reason. If we happen to trigger the mode button right as there is a rising edge in the run clock, we could create a metastable state here on this signal, which would propagate to our multiplexer and then create a glitch in our output clock. The solution is the same. We will just use double flopping and add a second flip-flop here triggered by the run clock, and then this will give time to the signal to stabilize. And there we go. That's our new mode selection circuit. Okay, and if we update our computation here to know what the maximum frequency of the clock is, we find 9.74, which is a bit lower than the maximum we can get here with our divider setting. But one thing that's actually been bugging me is we don't really need to go to 10 or to 5 megahertz with this circuit. My computer goes to 4 megahertz as a maximum. And so we don't actually need to get a 20 megahertz oscillator here. We can actually just make this 8. And so this gives us a maximum clock of 4 megahertz for the fast clock and satisfies the maximum frequency that we need for the selection circuit. Okay, let's go into the breadboard and implement those changes. Actually, one last thing that occurred to me is if we make the change for the maximum clock here to 4 megahertz, then we probably don't actually need the AC version of this chip here. And removing an AC chip is always a win because those can cause problems on breadboards. So if I replace this with the HC version, then my computation changes, which makes the maximum frequency 5.31. And so this works with our 4 megahertz maximum. Okay, this is much better. So let's get started. So the thing we can do is yank this oscillator. We won't need it anymore. And I can just take the one from the breakout board because this one is not in use when the debug clock is connected. Now we need to move the clock LED to the OR gate. And by the way, I'm just realizing I haven't pulled up the unused inputs here. I'm going to use a temporary connection because we're going to rewire the middle section in a minute. And there we go. And we can use the newly free inverter to invert the pulse clock. Okay, so let's try this. Power is back on. We're now on the fast clock, that this is working. If I switch mode, we are on the pulse clock. And the clock is low at the moment. And this one is not working. Did I invert the polarity? Yes. Okay. And then we need to update this here because we want to take the non-inverted clock as an input. There we go, so I've changed my DuPont connector to have a space in the middle, and that gives us the right pinout to connect here. So let's see, now the clock is high. Yep, that's correct. Now we have to rewire this middle section here to work with our bit select changes. You've seen me rewire this breadboard a couple of times already in this series, and so I'm gonna speed through it and let's speak again when this is done. Alright, so this section has been rewired, and it seems that everything is working properly. So the CPU is working, it's printing to the screen. I can switch to the pulse mode and pulse the clock. You can see it pulsing here. And I can go back to fast clock and then go to slow clock. And then we have the slow clock here. So yeah, everything is back to working properly. Okay, so now that we've improved the debug clock, the next thing I want to look at is the debug module. We have this LED array here that takes a bunch of the signals of the CPU and shows them on LEDs. And there are a number of other signals that we currently don't have an LED for that would be nice to display. So I've came up with this scheme right here, where I'm using the existing 10 LED bar and I'm adding a second 8 LED bar with the following color scheme. And I've mapped signals to where I think they would make sense in the build. So let's update the debug module to take this into account. We can use the same values of resistors depending on the color, as the LEDs are identical to our previous modules. The only thing that we have to keep in mind is that because I want them in this orientation with the red on top, I have to rotate the LEDs, and so we need active low signals on this side. So this would work except for these three. So let's see how we can invert them in a minute. All right, so I've fired up the new LEDs here, and they're all working. I've tested all of them off camera, so this was a lot of wiring, so I didn't want to bore you with cutting all those wires. One other thing I wanted to do with LEDs is I'm going to add some more of those 8-bit LEDs here to show the values of the data ports on the VIA. So let me do that now. Alright, so the LEDs for port A and port B were already in the file. We had them before, they just got removed during the most recent rewiring. So we just have to add the same arrangement here for CA1, CA2, CB1 and CB2. So let's just copy everything and paste. We'll make the LED green. There we go. And then the rest we can connect to ground. Okay. All right. So I've added some new LEDs here to show the status of the ports on the VIA. And I have 4 LEDs left here on this 8-bit module that I want to use, and what I'm thinking is I'm going to move the status LEDs for the ACIA, which there are 4 LEDs, to this here. So I'm going to do that now. So now there's 4 signals here. We could take the LEDs for the serial communications, so those ones, and we use this display. So I guess we have to export the signals between the sheets. So let's label them. And I made a mistake here calling this TX because it's TX from the point of view of the MCP2221A. And so this is what the computer is actually receiving. So better call this RX. Okay, so let's take this and add output labels. I actually want to add some color here, and for that I will take this LED here that we have in the debug module. We have the 4 green ports for CA1 to CB2 here. Then we have red for the USB configured status. We have 2 yellows for RX and TX, and then another green for the I2C traffic. So I think this is a good color scheme. Now there is one last issue, and that's RX, TX, and I2C are low when communication is happening, and so we need to invert the signals in order for the LED to have the right polarity. And so we need 3 inverters, and we just by chance have those 3 here, which we can take. So and there we go. Now let's implement those LEDs in the circuit. Alright, so I've added a new 8-bit LED here. So the LEDs on the right are for CA1 to CB2 on the VIA, and then the LEDs on the left are for the status of the serial link. And you can see if I reset, not sure how well you can see that on camera. You can see the transmit LED turn on here when the string is transmitted, and if I switch to the slow clock and reset, you can see the computer talking to the LCD over the VIA. Alright, so I think I will end this video here. I'm pretty happy with how things turn out with this spring cleanup, because we've been able to improve a bunch of things. It was all small details, but I guess they all make the circuit a little bit better. In the next video, I will talk about interrupts on the 65816 and how we can use them to improve serial communications. In the meantime, if you have any questions or feedback, please let me know in the comments section. If you'd like to support this project and help me with the purchase of parts and tools necessary to make this computer a reality, you can support me on Patreon. I'll put the link in the description box below. And in any case, I hope to see you in the next video. Goodbye.